Question 1 is all the chemistry from this year. So if we take a look, first thing we're asked to do is look at bond energies. We've been given a balanced chemical equation. We've been given a number of bond energies. And before we carry on with this, we're going to need to actually draw the shapes of those molecules, because it's only with the shapes that we can understand which of these bonds that we are going to use. So, taking a look first at H2. H2, the molecule is a linear molecule with a single bond between the two hydrogens. I could have worked that out using Lewis dots, but this is just a simple Cooper notation. There are going to be 3 of those, which means that the HH bond is 436. And I've now accounted for breaking of those bonds. Then I also have got the nitrogen molecule, and the nitrogen molecule, if I do a Lewis dot diagram, I will see that there are 3 pairs of electrons shared. That's just your Cooper notation, and again I can go in over here and I can take a look at the nitrogen triple bond, which is going to be 941. There's only one nitrogen molecule, so that's the total. So these are going to be the bonds that have to be broken. If I add them up, I find that I get 2,249 kilojoules. That's how much energy I need to take in. So that energy has to be added to the system. Now, in terms of breaking bonds, I'm going to take a look and I'm going to draw the ammonia molecule. And if I draw a Cooper notation of the ammonia molecule, I land up with a pyramidal molecule, and I see that I have got over here nitrogen-hydrogen bond 389. So I've got 1 nitrogen-hydrogen, 2 and 3 of them. So I am going to say 3 of the nitrogen-hydrogen, 389. But I haven't only got 3, I've actually got 2 of that molecule. So I now need to multiply all of that up by a further 2. And I land up with an answer of 2,334 kilojoules. That is bonds made. So in other words, this is the energy that has been released. If I now want to get the total energy change for this reaction, I am going to need to see how much energy was released and how much energy was added. And I find that I have got more energy being released than added, and that means that I'm going to get a delta H value which is equal to the energy added minus the energy released. And that turns out to be a negative 85 kilojoules for that balanced equation. And finally, that tells me, since more energy was released than was added, state with a reason whether this reaction is endothermic or exothermic. Exothermic means that more energy has been released. So it is an exothermic reaction. So if I'm using carbon tetrachloride as an example, first thing I'm going to land up doing is I need to draw a Lewis dot diagram. A Lewis dot diagram says to me that I have got to go all the way back to first principles. So I am going to have a carbon in the middle. The carbon is going to have 4 valence electrons. Those 4 will have hybridized, so it's 4 lone electrons. And the chlorine in each case has got 7. So we bring those chlorines in. The single electron in each case goes into the bond. And there are remaining 6 in 3 pairs around that molecule. Put them there. That gives the carbon the illusion that it is neon, and the chlorine also has an outer electron structure with 8, which is giving it the illusion that it is argon. The shape of that molecule is going to be tetrahedral. You do need to learn some of the shapes. This is a classic shape where you land up with a symmetrical molecule. The bond between carbon and hydrogen is going, the bond between carbon and chlorine is going to be a polar bond, and it says that over here. So we've got carbon and chlorine having polar bonds, but overall this is a non-polar molecule. You need to word that carefully. You can't just say they balance each other out or something like that. You need to be a little bit more specific. So you need to say something about symmetry. So a good answer would include that the polar bonds are symmetrical. Therefore, equal electrostatic forces therefore you land up with them, forces cancel out. Without the word symmetrical, they can't be awarded full marks. There needs to be the idea of a symmetry of forces. Remember, what the polarity of a bond really is simply a force based on electronic charges and on their electronegativity. So you've got to show that you've balanced out the forces. Magnesium hydroxide is a white salt. Show by calculation that the relative formula mass for magnesium hydroxide is. So, if you get the wrong answer, best you relook at your formula, but let's look at the formula. We've got magnesium, it's in group 2, so it has a valency of 2. The hydroxide ion is in group, it doesn't have a group at all, it's one that you have to learn, and if we hold hands, we find that the formula for magnesium hydroxide is MgOH2. Now, I could have been sticky about seeing that formula and giving you a mark for it, but even if I didn't see the formula and you went on to do the correct calculations, you could have got the marks. So we're going to say that is equal to, magnesium is 24,3, and hydroxide is 16 plus 1, so it's 17, and there are 2 hydroxides, and altogether that comes to 58,3 grams per mole. If you get the right answer, I gave you the answer in this one, so it doesn't really help. You need to get the right answer by using the correct method. So I marked the method in this particular case, not the answer. Calculate the mass of magnesium hydroxide in 1,5 moles. So if we're going to calculate the mass, we're going to say mass is equal to number of moles times molar mass. They've told me the number of moles, 1,5. They've also told me the molar mass in the previous question. So even if you got a different answer, use their answer, and you get 87,45 grams. Next one says, how many magnesium hydroxide particles does that represent? So number of particles is equal to number of moles times Avogadro's number. The number of moles, 1,5. Avogadro's number, 6,02 times 10 to the power of 23. And I land up with 9,03 times 10 to the 23 particles. How many hydroxide ions are present? Now we need to take a look at the ratio between magnesium hydroxide and the hydroxide ion. Well, for every 1 magnesium hydroxide, I have 2 hydroxide ions. So for every 9,03 times 10 to the 23 magnesium hydroxides, I have got double that number, 1,8 times 10 to the 24 OH minus ions, hydroxide ions. So it's a ratio between the total formula and the number of that particular ion within the total formula. Then there's two definitions: distinguish between valency and valence electrons. In both cases, you're going to need to be quite specific, and you need to, whenever you are asked to distinguish, distinguishing means that you must try and find something that's a little bit common between them as well. So in both cases, it's got to do with electrons. So if I'm going to now distinguish between the two, I'm going to say the valence electrons is the total electrons in the outer energy level. So that's the valence electrons. But valency is the number of electrons that participate in bonding. And again, I've clearly shown that I understand that they are linked, but they are not identical.